So good morning and welcome to this short presentation. And so how many of you are freshmen and sophomore? So the rest of you are juniors, seniors? Okay. So what we're going to talk about today is okay, let me first introduce myself, Meng, and I'm the area chair for physical electronics or photonics. And I just took this position over from Dr. Trevor Thornton last semester. So this is the second time I'm making this presentation. I will explain what physical electronics photonics is about, and but also a little bit of background information. We have 30 faculty members on the physical electronics photonics, and now these 6 of them are actually in multiple areas, so they are not in physical electronics photonics only. And if you look at the ranking, we are pretty well ranked, number 37 by US News and World Report, and in undergraduate program. And you know that we have like 20 very good, very selective private schools ahead of us, so we are actually pretty well ranked. Actually, our president has been saying that we should be judged by who we include, not who we exclude. So I think that's really, yeah, I totally agree with that. And now, so let me first explain what is electronics, physical electronics. And you can see that it's the science of technology of materials, devices, systems that involve the control of electrons. And just to give you a little bit of history of how we have been progressing in physical electronics. These are I'm not sure if any of you have seen this. When I was a kid, I saw these like vacuum tubes. And my father had an old radio with like 5 or 6 vacuum tubes in it. When you turn on the vacuum tubes, there's a wire inside which lights up. And but these are really, really bulky devices which does what so this is the first solid-state transistor in all this, which does exactly the same function as these big, bulky vacuum tubes. And then the next step is that we put many of these small devices. Now this is not small yet. This is still like a half-inch across, and these are probably a couple inches in size. This is about a half-inch size. Then we put billions of these devices onto a single chip, which is about inch by inch. And nowadays we can put over 1 billion of these guys onto a single chip. That's why your computer is so, laptop is so powerful these days. So if you look at the system level, in the 50s, a mainframe computer takes the whole area of this room. Then by the 90s, 80s and 90s, we have this first desktop computer. Then now everybody, I don't even have a desktop anymore. I just have a laptop of about this size. And so the computing power of this laptop is far more powerful than that mainframe which takes the whole room. That's how much we have advanced in physical electronics. Photonics, that's the science and technology to generate, control, and detect light. But what's funny is that we understand what the light is, and these are all the lights. Without light, we will not be able to sit here and watching this presentation. But for engineers like me, what is light? Light is billions and zillions of particles. These particles, we call them photons. So that's why we have photonics. So now, in this case, instead of controlling electrons, now we control photons. And so one example is now this. I'm using a laser pointer and a green laser pointer. That's one of the newer products. And we also try to put a lot of photonic devices onto chip. That's called integrated photonics. And I will come back to solar cells a little bit later. And then all the communication, long distance communication now is through optical fibers. If you talk to friends in Japan, in China, in Pakistan, it's all optical fiber under the Pacific Ocean. And also here, even within the, say you live off campus and you log on to your computer and you are going through one of those optical networks under the ground in Phoenix area. Now, this is really my specialty now, and so that's why I added this slide. I used to work on these like physical electronics and for quite a few years. And then over the last 10 or 15 years, I am moved into photovoltaics. That's the science and technology to generate electrons from light, namely to generate electricity from sunlight. That's photovoltaics. So it combines of electronics and photonics. And now you have seen all the ASU parking garages on the rooftop. You have those solar systems. And if you look into those solar systems, they have many of like hundreds or even thousands or even tens of thousands of these what we call solar panels. Now, if you have a chance to hold a solar panel, and if you look inside, there are typically 60 of these solar cells. So this is about 4 feet by 6 feet in dimension. Then you will see 60 of these solar cells, and each cell is 6 inches by 6 inches. Then you have 60 of them in each module. Then these solar cells are made on these silicon wafers. So this is the wafer without any solar cell on it. Then you make a solar cell out of these wafers. Then you get the wafers to look like this. Then where do we get these silicon wafers? We start with very pure, ultra pure silicon. And we have a term called 7 nines, 8 nines, 9 nines. That's the purity of silicon we use. When we say 9 nines, that means that the purity of this silicon is 99.99999. There are 7 nines after the decimal point. So you have total 9 nines. So that's called 9 nines or even 10 nines, sometimes down to 8 nines. So that's how pure this silicon is. Then where does this silicon come from? Quartz. Quartz is starting material to make these solar modules. Okay, that's the photovoltaics. ASU actually is pretty strong in photovoltaics, and we have a national center on photovoltaics. Now, also really impressive on the electronic side. Each of your laptop contains about half dozen chips inside. These chips are typically like 1 inch by 1 inch in size. How many transistors are on each of these chips? Nowadays, they are on the order of 5 to 10 billion transistors. So this shows over the time the number of transistors per chip over time. So this is the number of transistors. We started with like 2, 3, 4 transistors per chip to nowadays, and this is only 2011. We are in 2019, so this is 80 years obsolete. But so now in 2011, we were already talking about 1 billion. Nowadays, we are actually further on this trajectory, so we're at 5 to 10 billion transistors per chip. That's why your laptop is so powerful. Okay, in old days when I have a vacuum tube, you really cannot imagine you put 10 billion vacuum tubes together to just consider how big a space that needs and how much power it needs. So that's all not on your laptop. That's all that computing power is on your laptop. This is the size of the industry. Again, the data is a little bit obsolete. And in 2015, the total semiconductor industry, the physical electronics industry is about $330 billion. And then you can divide this industry in different ways. And if you look at between integrated circuits versus discrete circuits, that means you look at chips versus individual devices. Then chips are $275 billion, and those individual devices are $60 billion. So most of the semiconductor industry is about the chips. And if you look at digital versus logical, then digital is the dominant industry, and most of the chips we make are digital chips. And also you look at device level, and most of device we make are what we call the metal oxide semiconductor devices. Most devices, so $230 billion out of $330 billion. Then out of these digital chips we make, and a third of them is memory chips. When you buy a laptop, you always worry about how much memory you have and how much RAM you have. Those are memory devices. Then the microprocessor, CPU, is another third of this market. And then this is something but you probably don't know. In your cell phone, in your like TV set at home or audio system, they all contain this logic chips, which is what they typically call digital signal processor. And that's the part of logic. So that's another third. So three of them together, it's about $230 billion. So that's how big the industry is. Now the photonics market, and it says that 2015 is $450 billion, but if you look at it, and the two big pieces of that market, one is the processing of the materials for photonics, then communication is another large piece of this. Then some of these, like I would disagree because they put the lithography on the photonics, but the lithography tool is really a tool, very critical tool in making those computer chips. So this should really go into the semiconductor industry, but I guess these must be photonics people who came up with this pie. And now the laser industry, now this is a laser. This is a laser, I'm using a laser pointer here. Laser industry in 2016 about $10 billion. So in my view, actually photonics is slightly smaller than the semiconductor industry. But that doesn't mean that it does not have bright future because it will expand rapidly. But I think currently it's still smaller than the semiconductor industry. But if you look at if the source of these pies, and these are photonics people, so they always take everything they can have they can claim as theirs. Okay, and so semiconductor electronics, photonics, and electronic systems are driven by semiconductor chips. And sometimes if you have an older laptop, you don't need it. You can try to take it apart to see the chips inside. And especially when it's old, it's a 5-year-old, it's really worth nothing. So you can take it apart to see what's inside. These chips perform analog or digital circuit functions, and the dominant is digital functions, but there's still a lot analog functions. For example, when I talk, there's a microphone here. My voice is translated into an analog signal first. Then the analog signal goes through a digital signal processor to become a digital signal. That's what's recorded on that camcorder. Okay. So we cannot live without analog devices, but most of the devices we have today are digital devices. And now if you look at these circuit functions, then they always involve semiconductor devices. And then these devices have to be designed, fabricated, measured, modeled, and marketed and sold, so you get into the material fabrication side. And so what do you need to know in order to be an engineer in here? You need to know the device physics, you need to know circuit design, you need to know fabrication technology, modeling, and measurements. But these are all engineering related jobs, but you also need to market them and sell them. It's frozen. Oh, okay, there's something else here. Good. Okay, and now just look at the ASU and what we have here. And we're looking at these materials, electronic, photonic materials. This is a very, very fancy piece of equipment. It's called a molecular beam epitaxy system, MBE system. Sometimes people call it molecular beam milling. I forgot that's the name, like a $1 million machine or something, like a molecular beam epitaxy called a $1 million equipment or something. So it's really, really expensive. This piece of machine is probably worth like several $1 million. But we have a couple of them here at the SU. And also, to do fabrication, you need a facility. So we have a national center on nano fabrication facility. Actually, Professor Thornton is the director of that center. And this is my research area and photovoltaics. And this is a single solar cell. But this is a really old picture. And if you are interested, you can come to my office. I can show you the latest solar cells companies make. It's look totally different from this one. And now this is a laser, and this is actually an interesting thing. That is, I'm not sure if you are aware, this green laser is a single wavelength light. Red laser is single wavelength light, and the blue laser is single wavelength light. But what's the way eyes are used to is like a natural light, which is a multi-wavelength light, like white. How can you create a white laser with which is multi-wavelength out of single wavelength? We have a Professor Meng actually works on that white laser. It's not an easy task because it has multiple wavelengths, and laser by its nature is a single wavelength device. So how do we get a white light out of a laser? So okay, what do engineers do in the semiconductor industry? And the circuit design, that's certainly part of it, and design and layout the circuits to be manufactured, simulation, modeling, and you need to understand the device, you need to design the devices, so you need to do simulation, fabrication, and maintain yield, maintain throughput. And also once the chips are made, you need to measure them and characterize them so they are good quality. Quality control is part of the sales marketing. So you can get involved in all of these jobs when you get go out and find an industrial job. So just here, just a list of some of our companies. Most of them are in the valley, but some of them are away from our Phoenix area. And in the semiconductor electronic device IC manufacturers, free scale, I guess that's pretty much gone, and on semiconductor, which is still has a headquarters here in Phoenix. Intel has quite a few fabs here actually in the valley. And Micron is I think in South Dakota, I forgot. And Texas Instruments in Dallas, and National Semiconductor is still around. And IBM is probably one of the biggest companies to work for. And Apple, Dell, they all have devices involved. Photonics industry, these companies are typically smaller than these companies. Cree is one, MCOR is another one, and I'm not familiar with these companies. And Raytheon has a division in Tucson here, and not far from here. Lockheed Martin, this spelling is wrong. This is Lockheed Martin, actually Lockheed Martin. And equipment manufacturers, we have quite a few equipment manufacturers. I think ASM has a division here, and Applied Materials is based in Silicon Valley, and KR Tanker. Actually, I have a lot of friends who work for Applied Materials. I have one of my students who actually went to KR Tanker, and in Portland, Oregon. And yeah, I have students working for Texas Instruments, for IBM, and for Intel. Quite a few for Intel, one for Micron. Yeah, Global Foundry. Actually, that student actually decided to go to Intel instead of Global Foundry, so he's with Intel. And I don't have any students working for these companies, and I have a couple of students friends working for these companies, and the solar industry. And we have First Solar. Now, if you drive from here to the airport, 202, you will see the building which says First Solar. That's their headquarters. But their manufacturing actually is in Ohio. And SunPower is in California. And these are smaller companies and services companies producing simulation software, other services. So now, what type of job can you expect when you graduate with a bachelor degree? It's more like entry-level degree. So for technical work, you will be at the lower end of the range of engineers. Basically, you have to climb the ladder from pretty much the bottom. Nowadays, for those semiconductor companies or photonics company, you don't have engineering degree, you will not get a technical job. But the bachelor degree is the really the starting point. So you basically climb the technical ladder from bottom. But the advantage of bachelor's degree is that it's more flexible. You can fit into a lot of different positions. They will always train you, spend 6 months or a year to train you. So you can be trained in different job categories, and so you are more flexible, but at the same time, you'll be starting from the bottom of the ladder. And sometimes you actually end up with less technical work. And the MS master degree is a very common degree for a lot of electrical engineers, computer scientists. You have more advanced knowledge, but you are not really specialized in a particular field. So when you get a job, you still need some training, but probably less training, especially if you do like circuit design. And with a master's degree, you can be a very good circuit designer. And so it's then also the company don't have to pay as high salary to you. And so PhD, now one good thing that's very, very specialized. You become an expert in a particular field. And so if you are interested in more advanced, more creative work, you need to get a PhD. Nowadays, if you want to get into like Intel's research development department or IBM research department, or you want to get any academic position without PhD, there's no chance. All faculty members have a PhD. Okay, so if it's really for more specialized advanced research, but once you get that, you do have the benefit of more secure job and higher pay. Now, this data is not really recent. I think this it doesn't have the time of this data. I will check. But at that time, and doctoral degrees, like a weekly salary is $1,600, and that's not far from professional degree. That's like a lawyer or doctors, medical doctors. So you are not far behind that, but you are far better than master's degrees and bachelor degrees. In terms of the unemployment rate, you can see that the lower your degree is, the higher the unemployment rate is. So you have more secure job, and especially for faculty positions, it's more like a permanent position. Once you are tenured, now like my position, you know when I would lose my job? Do you know? Retire is one option. I decide to retire, or I decide to quit. As you decide, we no longer need the electrical engineering department, then all the electrical engineering professor will lose job. But when would that happen if an engineering school does not have an electrical engineering department, or a university does not have engineering school? I would never think that's even a possibility. So pretty much the SU will always have electrical engineering. And so the only other possibility is that if I commit a felony, then SU can fire me now. Otherwise, there's no way SU can get rid of me. So, okay, the courses required for in solid state area. We have a couple of, these are all electives, but if you want to get into physical electronics, photonics, these are the courses you want to take. 434, I'm confused myself. Quantum mechanics for engineers. It says the quantum world is fascinating. Let me give you one example. What happens in quantum world? Now, if I bump into this wall, you know what happens? I get bounced back, right? If I'm an electron, this wall, you know what happens? I will be on the other side of the wall without damaging this wall, without breaking down this wall. That's quantum mechanics. So it's really fascinating, actually. It's called quantum tunneling. And 435 fundamentals are CMOS and MEMS, and the CMOS is really the basic device in computer chips. So that's what we call the building block for chips. And the fundamentals of solid-state devices, that's the physics and how these devices work. Optoelectronics is the first course you take for photonics. Then semiconductor facilities and clean room practices. Now this is really about manufacturing, how a clean room. I'm not sure if you have a chance to visit like the Intel's fab here in the Valley. These fab, the price tag of fab nowadays is close to $10 billion each. They spend a lot of money to build those fabs. And I think a couple of years ago, Intel had a ad on TV when somebody was dressed in bunny suit and with face, eyes, hands, hair all covered, and that's how you work in clean room. Yeah. So I think one of the reasons I did not want to continue to work on physical electronics was that when I wear those gloves, I sweat so much. Like after an hour, it's totally wet, and when you pull that off, you can drip water out of it. So that's why I decided, okay, that's probably not for me. But that's what's required if you work in clean room. And they spent $10 billion to build that facility. The worst nightmare for them is that you somehow, the whole purpose is to keep everything clean. So if you use your finger to touch something, and their yield will go down significantly. So they really don't want that to happen. So that's why. And then photovoltaic energy conversion, I taught this a couple of times, and we really need to look into sustainability. Okay. Is this the last slide? Yeah, this is the last slide. And if you have questions, and I can answer your questions. But I also really like to show you another presentation I made to my class this semester. This is for, come on. Why it does not allow me to? Okay. Now, I'm not sure how many of you heard of this Fulbright program. No? How many of you are international students? Or domestic students? Okay. So yeah, this probably makes sense to you. And the Fulbright program is let me skip this. Actually, that's how it's structured. Last year, I took a sabbatical, and I spent 2 semesters in Sweden, Chalmers University of Technology, and now when you take a sabbatical from SU pays like half of your salary, so you make up your salary, lost salary. So I got a major award from the State Department and Fulbright Distinguished Chair in Alternative Energy Technology. That actually makes up more than half of my salary, actually. So I made more money last year than this year. And each year, United States send about 15 to 20 of its citizens to Sweden. At the same time, Sweden also sends the same number of Swedes to the United States. So these are some of the Fulbrighters last year, and this was taken at the U.S. ambassador's residence in Stockholm. So I think there are 3 distinguished chairs here, me and Frank and Tom. And then this is scholar. Scholar means after you get a PhD and you get a scholar position. Then the rest are all students, just like you. But typically, now you need to plan this ahead of time, but typically you apply this the senior year. So if you want a gap year and between graduate school or your job and your bachelor degree, that's time you do that. So all these are like with their bachelor degrees, and then they spend a year in Sweden. And also the purpose is, do I have that? Yeah, I should read. What this program is about. It's named after Senator Fulbright. He spent quite a few years in Europe between 1924 and 1928 as a Rhodes Scholar. That's a UK foreign exchange program. And so he understands the importance of international exchanges. So in 1945, he proposed a bill, and it passed through Congress and signed into law in 1946 to have exchange with foreign countries. So the purpose is to increase mutual understanding between the people of the United States and people of other countries by means of educational and cultural exchange. So this program has been in existence for over 70 years, and it's always 2 exchanges. So we send Americans out, the other countries send their citizens to the United States, and over 160 countries are participating. So you can pick up almost any country and you want to go to and then get it funded. They cover all of your travel and living expenses, and so it's just experience for you, and you make friends there, and then you know that country a little bit better, and they know America a little bit better. Okay, so that's the whole purpose of this. And so, yeah, I should have these slides backwards. Now, if you are interested, and you can come and see me, and there's a website, and I also can give you a little bit of insight about of how to apply and how to improve the chances of your application. Okay, and we don't have scholars here, so scholars has another website. Now, just give you, now let me go back to a little bit of what I did there. Cultural exchange, education exchange. So I was visiting France and at the French National Lab and also University of Paris. That's one of the best schools in France. I was giving seminar there. Now this is a building, what they call green building. This building during daytime, it generates more electricity than it consumes. This is in Toulouse, France. They also want you to travel as much as you can. So we went to the Arctic Circle in January in Sweden. This is Northern Lights. First time in my life. We did dog sledding. I'm not sure if you know what this is. Every October, I think late October, early November, they cut ice from lake and then build a hotel with ice. And then you can actually sleep there. If you have like a $900 a night, you can sleep there. And then by March, April, the hotel melts. So next year they build again. It's called Ice Hotel. And initially I was thinking we should sleep there just for one night. But our kids went with us, so they could not finalize their schedule. So I waited until like, we went there in early January. So they told us, okay, we can come in early January, but like in late November. So by that time, if you reserve it in September, it's like $300 or $400 a night. But by November, it's like $900 a night. And I thought, wow, that's way too expensive for me. So we went there. But you know, I was glad that we did not live there, because the room you cannot heat the room because the ice will melt. Yeah. There's no restroom in it. So at night, if you want to go to the restroom, you put on everything you have, then walk 2 kilometers, 3 miles, or 3 miles, then to find the restroom at night. So it's really not a comfortable experience if you sleep there overnight. But it's just really fascinating. Now, Sweden is building another very fancy hotel. They are building a hotel on a lake. They say that hotel will be ready maybe in 2019 or 2020, I don't remember the exact time. So you can actually also live in a hotel which is right on a lake, in the middle of a lake. So this is another attraction in northern, it's called Kiruna, that's a small town in northern Sweden. So it's a very, very nice experience. But the highlight of my sabbatical is really, I was invited to the Nobel Award ceremony in 2017 in Stockholm. And this is invitation individualized. So they put down your name. So when you go in there, you have to bring your passport. They want to make sure you are the person who's invited. And also they have very strict dress code. Actually, if you look at Swiss, what they take is that they have this penguin suit. There's a tail on the back side. And they have this, actually you need to buy a white bow tie, not the black bow tie. The problem in Phoenix is that you can go to any department store. There's no tail suit to find. There's no white bow tie. So this is as close as I got. And also it's quite expensive actually. This suit cost me like $2,500. My wife's got like $1,500, so $4,000 for that one night, 2 hours. But now, what do you get out of it? I not totally understand that English word called impact, I-M-P-A-C-T, impact, the impact of your research. Those are the people who get Nobel Prizes. These are actually really, you can hear what their work, what kind of impact their work has. So they do change everybody's daily life. So that's what I got out of it. So it's a really, really exciting experience. So I just want to share that with you. And then, okay. So questions now? Yeah.
You do any research?
Yeah. If I don't do research, then my chair will kick me out. No, will not give me any raise, I guess. Yeah. Research is like our job involves three laws: teaching, research, service. So research is an important part. Yeah.
What do you do research on?
Solar energy. Yeah, how to use solar energy, how to make solar energy cheaper, more reliable. And actually, what I focus on is sustainable solar technology. Yeah, a lot of people have a misconception that solar energy is sustainable, but actually, if the technology to utilize solar energy is not sustainable, we don't have sustainable energy. So that's what my research focuses on. Yeah. Oh, screen disappeared. Yeah. Yeah. Yeah.
I was trying to do power systems, but would you think like renewable solar energy is probably going to be better in the future than power systems?
There are two sides of the same issue. That is, we need more solar energy. Then this new energy source has to be integrated into power system. So the power system have to be able to deal with this unpredictable energy source. In the past, you have a nuclear or coal-fired power plants. That generation is always predictable, controllable. But with solar energy, you don't know next minute how much solar energy you will get. So the power system has to be able to deal with that. So that's actually, it's the same, it's just two sides of the same issue. Yeah.
So where do most PhDs in the workforce work? Like, is it mostly like research labs, or like where else would?
There are a couple of options here. You can go to a university faculty position. You can go to national labs. The Department of Energy has a lot of national labs. The Department of Defense also has a lot of labs. And you can also go to industry. This is one thing why American companies are so competitive. Those companies hire a lot of PhDs. And one time I was visiting many years ago, 1995, I visited the Intel's Portland Research Center. And I got my PhD from Illinois, and when I was visiting there, they were telling me that, okay, we have 300 Illinois PhDs here. That's 1995, and so they call them Illinois again. And so you see that that's just one site for Intel that has from one school 300 PhDs in that school. So it's that's why Intel is so competitive. And I don't think any company in the world can really compete with Intel. Yeah, but that's also true for a lot of other companies as well. Yeah, so you can go to industry, you can go to national labs, you can go to academic positions, so there are multiple options. Yeah, I have seldom seen a PhD without a job in my life. And now, of course, sometimes it takes a little bit longer for you to find the best fit. Yeah, because if they want somebody in that area, if you are slightly different from that area, they typically don't want to spend that time because they don't want to train a PhD. And so it probably takes you a little bit longer time to find your fit. But once you find your fit, then it's a very stable position. But bachelors are much more flexible. So when you come in, just see this kid is smart, works hard, and has good ethics, that's it. I take you, I will train you. But a PhD, they will not say, well, I will train you. So you need to have the right fit for that position.
And then what about masters? Is like right in the middle?
Masters is in the middle. They are still more flexible than PhDs, but they are more experienced than bachelors. So actually, a lot of positions, they actually like masters. So Of course, you have to be flexible as well. You cannot, if you don't have a PhD degree, then you have mindset, I have to do this job and nothing else. And that's not a good mindset. Yeah. Yeah.
Would you say that like physical electronics part is still being developed, or is a lot of places trying to look more into photonics area?
Yeah, that's a good question. Very good question. I think in general, photonics probably has a faster growth rate than the physical electronics, and because there are more applications being developed for photonics, and physical electronics is a little bit more mature because it started in 1945, right after the World War II. Photonics only started about the 1960s, 1970s. So, yeah. Yeah, but on the other hand, I'm not expert in photonics, so yeah, I don't know too much about that. Yeah.
Are there many graduate courses in the area of photonics?
Yeah, we have a photonics center here. Yeah, so we have it's a good question. How many courses? I need to pull up the website, and it's all you go to ECE website. All the courses are listed there. Then photonics is 530 something and 560 something. So you are interested in photonics?
Yeah, I'm looking into it.
Looking into it, yeah. This is certainly the time to think about what career path, what field you want to be in, what career path you want to take. And one thing I noticed is that different kids have different skills, different areas they are most interested in. So that, anything you do, it has to be something you have passion. With passion, you'll do a good job in any position you take. But if you don't have passion, then that's a different story. So how many of you have decided to go into a particular field? No, still open. Yeah.
Think about power.
Power, okay. How many of you are interested in power? 1, 2, 3, okay, yeah. How many of you are in physical electronics? Kind of, okay. Yeah.
If I went to physical electronics, would I have to take more classes hardware related then?
More semiconductor physics related class. So 434, 435, 436 to 440. Yeah. Now, power system actually is also another area I'm kind of moving into, because in the past you need to produce more efficient solar cells. You need to reduce the cost of solar cells. Now the cost is quite low, the efficiency is quite high. Then what's the next step? Next naturally is how you build a system out of those cheap and efficient solar cells. So that's kind of getting me into power system. Yeah.
So what would you say is like the main difference between like mixed signal circuits and like physical electronics?
Mixed signal circuit design is more of those devices. You need to connect them in a particular fashion for them to function. And you cannot randomly put a billion transistors into a basket and shake it and it will function for you. They have to be connected in a particular way. So circuit design is how you connect them. And so circuit design is more of, it's a little bit like a programming. So you basically sit in front of the computer using a simulation software to do that. But you will have, now typically these comes in modules. So this module does this function, that module does that function, and then you put two modules together, they do a new function. That's part of circuit design. Then get to a little bit, now I'm teaching a circuit class this semester. Then those modules typically has millions of transistors in it for very complicated chips. But you can also get down to like a power system circuits. Those are much simpler. Those only have 10, 20 devices, but issue is going to be much bigger. And then you involve how you design that circuit, how you connect the individual components together to have a particular function. Yeah, so that's part of my research actually what we're doing. So yeah, I have one student who went to Intel to do circuit design a couple of years ago. Yeah, so now my student does end up with like physical electronics, end up with circuit design, and my next student, Joe Azzolini, probably will end up in power systems. So that's just the nature of research here. So how many of you are seniors now? No seniors, junior? Okay, one couple of the juniors. Yeah. So you haven't decided a specialty yet, okay? Specialization. Okay. Yeah, let me know if you have questions. My office is Engineering Research Center, room 157. And you can send me email and we can schedule time if you want to come and see me and talk about what you want to do. Okay, and yeah, I'm quite familiar with the different areas in physical electronics, photonics, and if I don't know the answer to your question, and then I can certainly refer you to the right professor to talk to. Okay. Okay, and what time is it? We still have a couple of minutes actually. We're supposed to be an hour, right? Yeah, we can go a little bit over now if you want, but if you... Yeah, if you don't have questions, then you are free to go, but if you have questions, we can stay here a little bit longer. Yeah?
Which area of research did you do for PhD?
That's actually depending on which professor, who's your advisor. Different professors have different specialties, and we have almost 80 professors in the department, so they all work on different areas. And now currently, if you talk about research, and you need to look at the areas which has issues which we need to solve. Those are typically in energy, in sustainability. And then like a circuit design is more like industrial type position. There's not much research going on, but you need to design circuit for a particular chip, and that's industrial. So that does not really involve much research, but more development. Yeah. So it depends on what your interest is, which area you are interested in, and then you talk to those professors, and the professor probably will identify your research area, research topic. Yeah. Okay.